Hi, in this video, we're going to take a look at how common is it for Friday the 13th to come up. All right, so Friday of this week in a few days is going to be Friday the 13th. And, that got me thinking, how common is Friday the 13th? So, of course, I could just go look this up, right? I could just go and find this, but there's a more interesting way, a more interesting approach is that I could go use R and actually generate data to check this out. Now, something that's kind of interesting about this is that when I choose my start and end dates will impact the conclusions that I get. All right, so if I want to go all the way back to when the Catholic Church accepted the Gregorian calendar, I will get a different result if I choose the start date as when the British adopted the Gregorian calendar. Also, like how far out in the future do I go, or do I even go into the future? Do I stop at today? All these will slightly impact my conclusions. What I chose to go with is 1752. That's the year the British accepted the Gregorian calendar, and I stopped at 2024, the current year. So I'm in the United States. The United States effectively, before it was the United States, effectively accepted that calendar in 1752 when the British did. Okay, so let's go ahead and take a look at how I'm going to generate the data. So first and foremost, I clear my workspace of any gunk I don't want. I prevent too many things from being printed out. Don't want too long of decimals. Make sure there's nothing I don't want to see. And I'm going to be using piping quite a bit on this. So let's get the McGritter package. All right, so first and foremost, let's look at how dates are represented inside R. Now, so here, this is going to give me the system date. So this is the date that R believes is today. And so I made this, so I ran this today. And so it's September 11th, anniversary of that in addition. And it's 2024, September for 09, and then the day is 11. So in this format, we always go year, month, day. Okay. And so 0911 is September 11th. All right. Now, under the hood, our store's dates, the actual day itself, not date time, but dates as integer values. And there's going to be a reference point in every different system. So if I'm using SAS or SPSS or Python or R, are going to have different reference points. So since we're dealing with dates, it's always good to know like what is the reference point. So to figure that out, I'm going to take the system date here, and I'm going to convert the system date to the integer value. Now, if I take a date and I subtract or add an integer, I'm going to move the date appropriately. So if I add one, that's tomorrow. If I subtract one, that's yesterday. And so if I subtract today's date, I'm going to end up getting the system reference date, which is 1970 New Year's Day. Okay, so that just gives us a feel for how dates are stored within R and handled, and I'm going to use that, that subtraction aspect and addition and subtraction effectively to be able to generate all of my data. Now, according to Wikipedia, Britain and the British Empire, including what would become the United States, adopted the Gregorian calendar in 1752. I'm an American, so I'm going to say 1752 is my start for this. And I'm also going to do complete full years off of this because it just makes more sense. If I, did, halfway into a year or, just one quarter in, that would impact my analysis. Just for interpretation, I'm going full years on here. All right, so I've got 1752. New Year's Day is what I'm going to use as my start, and then I'm going to set my end date as New Year's Eve of this year, so 2024, December 31st. Okay, now how am I going to get all of the dates in here? Is I'm going to just do a sequence starting from the date that I want for the beginning, date that I want as the end, and do a by statement of 1. And so then it will go through and go from New Year's Day, 1952 all the way out to New Year's Eve 2024, every single one of those days. Okay. And so now, after I've done this part of the piping process, well, this gives me all of the dates. Then I'm going to have this within a data frame. From this, I can go ahead, use piping, and I can get the year off of the date. I can get the month, which will be 1 to 12. I can get the day of the month, and I can get the day of the week off of here. So here, M day is day of the month. W day is the day of the week. Now to put these together, because I want Friday the 13th, so I want the month day to be 13, I want the weekday to be 6 off of this. So we're starting with the days of the week. Sunday is 1 and Saturday is 7. So Friday is 6. So how I'm going to go about this is I'm going to put these together into one column. I'm going to call it M day, W day, to make it as explicit as possible. It's matching up. And I'm going to, first and foremost, I want to paste them together. So this is also called concatenating the string. I'm going to put a hyphen in between them. Now there's something a little bit different that I do here on the string R step. Here, I'm making sure that I have 2 digits for the day of the month by putting in a 0 if needed. So if the day of the month is 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm changing that to 0, 1, 0, 2, 0, 3, 0, 4, all the way out to 0, 9. All right, so why do I do that? This sets it up so that if I need to do any sorting, the dictionary order of the string matches the numerical order that I want them to give. All right, and so now I'm going to create a column called Friday the 13th. Hopefully Jason approves. And I'm just going to say, hey, if the month day weekday is equal to 13/6, then it's going to be a true, otherwise it's going to be a false. And then I'm adding 0 to convert it to zeros and ones. All right, so this is going to be a binary column for me, a binary indicator. All right, so let's go ahead and just take a look at the data, make sure that this makes sense. Did I get what I intended at the top of the data? All right, so 1752, New Year's Day. All right, that's the right year, right month, right day of the month. Now, it looks like that was a Saturday. Okay, I honestly don't know one way or another. I guess I could check, but I'm not going to bother. And clearly, all of these are not Friday the 13th because they're too early in the month. So appropriately, I have all zeros. Let's take a look at the tail of the data frame. And so here I've got that last day that I intended. The year is correct. The month is correct. The day of the month is correct. Now here, this is saying this is Tuesday. So New Year's Eve was a Tuesday, will be a Tuesday this year. I didn't check it, but I'll assume it's right. And here is that M day, W day format. And none of these are Friday the 13th, so because they're too late in the month. And so it's all zeros. All right, things look good. Now, there's questions about leap years. Remember that when we talk about leap years are always divisible by 4 unless it's divisible by like 1,000, something like that. So, no, if it's divisible by 4, it's a leap year, unless it's divisible by 100, unless it's divisible by 1,000. So it like bounces back and forth like that. And there's some really cool math and describing like with nested fractions to show the mathematics of this. But I want to double check this and verify. So what I'm going to do is I'm going to take a look at every single time that the month is February and the day of the month is the 29th. So here I only want the times that a leap day occurred off of here. So what I'm doing on this step, I'm double checking to make sure that my data is correct. All right, so I see that I've got multiples of 4, multiples of 4, multiples of 4. Now you'll notice when I get to 1800, it's not in there. Okay, good. That's what I wanted. 1800 is missing, even though it's divisible by 4. Let's keep on going. I see divisible by 4 all the way down as I'm scrolling through. And we'll notice when I get to 1900, that's missing also. Okay, so that is correct. 1800 and 1900 should not be in the data set. Also, 1700 wouldn't be also, but I started my data at 1752. So it's not coming up. Now, here is the year 2000. The year 2000 was a leap year, even though it's divisible by 4. So, yeah, or even though it's divisible by 100. All right, so then, we just see our results. Also, you'll notice that every single time I do not have Friday the 13th, which is absolutely correct. Okay, so now let's go ahead and just double check this. So I know that this should not be in the data set. This should not be in the data set, but this one should be in the data set. I check, and yes, it's exactly how it's supposed to be. So I have confidence in my data. I believe I can proceed with my analysis. All right, so overall, what percentage of days in a year are Friday the 13th? Okay, well, I can do that real easily by taking my full data set and just taking the average of those zeros and ones for the Friday the 13th, and boom, I can see it's a little bit less than 0.5%. Huh, I mean, that's interesting. Now, how does that compare to just, like what percentage is one day of the year overall? And we can see that it's, a little bit more than 1/5 of a percentage. So, Friday the 13th is more common than one single day. Okay, so now on average, what percentage of Fridays are Friday the 13th? So if I say, hey, I want to know what fraction of Fridays are Friday the 13th, what I'm going to do, I'm going to limit my data to Fridays, and then I'm going to do exactly the same calculation I did before, and we can see that approximately 1/3 of Fridays are, sorry, no, a third of a, sorry, 3%, a little bit more than 3% of Fridays are Friday the 13th. Okay, that's kind of interesting. Now, on average, what percentage of the 13th day of the month is a Friday the 13th? All right, well, I can do the same trick, but now I'm filtering on the day of the month has to be a 13th. It has to be 13, and we can see that it's 0.143. And honestly, that's about 1/7 if you double check that. Now, which years had the most Friday the 13th? Okay, well, what I'm going to do is I'm going to group by year. I'm going to take the number of Friday the 13th that each year had, and then I'm going to limit the data to years that had the maximum amount. And so we can see that all of these years, 39 years in, or sorry, 39 years in the data set had 3 Friday the 13th. Huh. What about the fewest? Okay, well, on that one, I'm going to do the same trick. I'm going to group by year. I'm going to take the sum of the Friday the 13th indicators, and then I'm going to restrict my data to the minimum. And we can see that now it's far more common to have exactly one Friday the 13th, 115 years in my data set. All right, now here's a good question. We want to know which month have the most Friday the 13th. Okay, well, let's check that out. So here I'm going to group by the month, and then I'm going to do the sum just like I did before. And we can look through, see we have 40, 40, 40, 40, 40, 40. So we see December, that's September, July, April, and May, and then January in the range of data that I selected. So remember, I started at 1752 to 2024. If you change the start and end dates from what I have, you'll get different numbers here. So, just kind of be aware of that. What about the least? Which month has the fewest? Well, on this one, that is what, August. All right, so this brings up a question of like, how many yearly patterns do we have for month, day, and weekday? Because all this analysis, I'm looking at month, day, and weekday. How many possible results could I possibly get? Well, just thinking about off the top of my head, we would have, what day does January 1st land on in the week? And then is it a leap year, yes or no, would dictate the entire results of, the combination of month day and weekday. Okay, so let's go ahead and check, does this make sense? That would be 14 possibilities. So what I'm going to do is I'm going to take every single month day, weekday for each individual year. So here I am taking each year's month day, so I'm taking each year of the data frame. I'm taking only the month day, weekday pattern that it has, and then I'm looking at only the unique ones, and then I'm counting the number of unique patterns we have, and we have 14, so it's exactly that way. All right, and so now let's see, which patterns have. So if I look at all the unique patterns, we can see that there are 6 that have 1 Friday the 13th. There are 6 that have 2 Friday the 13th, and 2 that have 3 Friday the 13th. So if we see that we have a year that has 3 Friday the 13th, that's kind of a a little bit kind of rare. 2 out of 14, 1 out of 7. Having 1 or 2 is far more common. All right, I hope you've enjoyed this. I think this is interesting. If you don't believe me, test it, evaluate it. I'm showing you how to generate the data. You can verify or reject my conclusions easily by using this. I'll go back to the part to generate the data, and so to work through this, you just have to choose the start date and end date as you see fit. So for example, you could start like the year that the Catholic Church started using the calendar, and you could go out into the future to a day that you prefer, or go limit to today, whatever works best for you, and verify or reject what I got. All right, well, that's all I've got for you. Life is short. Do math.